Hi, and welcome to NCTV's Climate Changes. I'm Leslie Smith, and here with me are Alan Stoller, Lianna Smith, and Lew Sitzer. This is the second show in a series designed to inform our viewers about the science behind climate change, what resource managers are doing to prepare for long-term climate change, and what we as ordinary citizens can do to limit our contribution to an increase in global greenhouse gases. In our last segment, we introduced the difference between weather and climate, climate being the long-term weather patterns of an area. The climate of Nevada County is temperate. It lies between the equator and the poles, and it doesn't experience the extremes of either place. Scientists have gathered convincing evidence that indicates Earth's climate has gone through major changes throughout its history. The leaves in this first slide tell us a story about a region's climate history. The leaves you see here have smooth margins or edges. Leaves with smooth margins tend to live in tropical climates where it is warm and humid. Leaves in more temperate zones, as in Nevada County, tend to have rough edges. Fossil leaves found in the Chalk Bluff area of Nevada County have smooth margins, suggesting that the climate of Nevada County was once warmer and more humid than it is today. Other evidence of historical climate change is found in the annual rings of trees. Annual rings reflect the growth of the tree and give us clues about precipitation and temperature. Ice core samples also provide evidence for temperature of Earth. In this program, we'll be looking at the roles of atmosphere and the oceans in regulating Earth's climate. Let's go now to Alan, who's in the field, and he'll talk to us about the Earth's temperature.
The sunshine I'm standing in feels great. It's warming me up, it's warming up this wall, it's warming up the whole Earth. The Earth would be a giant ball of rock and ice were it not for the sun warming it up. This wall has been bathed in sunlight, it's been absorbing that light. That light has warmed up the wall, and the wall is now glowing. It's not glowing like the sun, it's not hot enough, but I know it's glowing because I can feel it. Just like when I put up my hands to a wood stove, I can feel the warmth. Here again, it's glowing, not in visible light, but an infrared. Infra means below red light. Rattlesnakes can see infrared, but we human beings can't. But we human beings have cameras that can see infrared. Let's head back into the studio and look at some images. When the Apollo astronauts were training to go to the moon, they were given a list of rules. One of those rules for moonwalkers was, don't sit down. When the sun sets and night falls on the moon, temperatures drop like a rock down to something like minus 300 degrees Fahrenheit. When the sun rises again, temperatures shoot back up to a toasty 250 degrees above zero. What would happen to the plastic and rubber in an astronaut's spacesuit if he were to sit down on a 250 degree rock? Never mind his spacesuit, what would happen to his butt? Even without sitting down, walking on 250 degree rocks is hot work, which is why, besides carrying oxygen in their backpacks, the astronauts also carried a refrigerator for making ice water, which was then pumped through tubes in their long underwear to keep them cool. Earth is exactly as close to the sun as the moon, but even Death Valley doesn't get nearly as hot, nor does Antarctica get nearly as cold as temperatures on the moon. Earth has air, we have an atmosphere. The moon has no air, no atmosphere. Air is a fluid. It can flow from one place to another. When you have air, you get wind. Wind redistributes heat around the Earth, from the day side to the night, from the tropics to the poles. So the warm parts of Earth don't get nearly as hot as they might, nor the coldest parts nearly as cold. Our atmosphere does more than just even out the extremes. If you take the average temperature of the moon, day and night, it's close to 0 degrees Fahrenheit. But if you take the average temperature of the Earth, it's up in the high 50s. Our atmosphere is mostly nitrogen and oxygen, gases that are even more transparent than glass, letting sunlight bathe the Earth. Like that wall sitting in the sun, the Earth gets warm, and like that wall, it glows in the infrared. Oxygen and nitrogen are just as transparent to infrared radiation as they are to visible light. But other gases like water vapor and carbon dioxide, are not transparent to infrared. They're opaque. They absorb infrared, they get warm, and they pass that warmth on to the air around them. It's these so-called greenhouse gases that give our planet an average temperature roughly 60 degrees warmer than the moon. When it comes to warming the atmosphere, one greenhouse gas stands out above all the others. It's powerful, and there's a lot of it. It's gaseous water vapor. Here we're looking through the lens of an infrared camera at a dog. His eyes are warm, but his nose is cold, and where his fur is most insulating, keeping most of his heat in, he's coldest of all. We can make the same sort of infrared picture of the Earth and see where the Earth is glowing brightest in the infrared, as we can see in this image from an orbiting spacecraft. Here, the red color shows us the eastern Pacific warming up at the start of an El Nino episode. When we burn fossil fuels, we inject huge amounts of carbon dioxide into the air. Carbon dioxide is also a powerful greenhouse gas. It will warm the atmosphere, which will suck more water vapor out of the oceans, off the land, from trees and shrubs and grasses. One of the many questions involved in the climate change debate is how much will water vapor warm the future atmosphere? How sensitive is the climate to extra greenhouse gases? Let's look first, though, at another of Earth's fluids, the ocean. Lew?
Thanks, Alan. Before we go on to the oceans, I wanted to take a moment to inform our viewers as to the real experts in science on this panel. Leslie and Alan have been devoting most of their life to the study of science, and we really lean on them for more of a scientific perspective. Lianna and I have our recent devotees of climate change, and we took it on because of the urgency we felt that is apparent in the climate of our planet. So I wanted to talk about computer modeling because that is the way in which scientists have been dealing, one of the ways in which they have been researching climate change, and that is through computer modeling. And you may hear this term throughout not only our show, but articles and other shows that you come across. Well, computer modeling is something that the International Panel of Climate on Climate Change through the United Nations has been using dozens of computers to help to study the past and also predict the future. So there is a degree of uncertainty with computer modeling, but the weight of evidence has led many scientific groups to form conclusions that are the basis of the urgency in dealing with the issue of climate change. So we're going to be talking about the ocean and ocean currents, and if we could go on to the first slide, this indicates the ocean currents and the way in which surface winds are created. Now 70% of the planet is occupied with ocean and 30% landmass. Of the ocean surface water, the surface water of the ocean has 98% of the total surface water of the planet. And this surface water warms and forms a temperature gradient as you leave the surface water and travel up into the atmosphere. The air cools. Sometimes clouds are formed through water vapor evaporation. Clouds also help to cool. The sun reflects off of the ocean, warming the ocean, and the temperature gradient between the ocean and the atmosphere helps to create wind. The differences between the temperature of the air and the temperature of the water helps to create winds which drive the currents And it's interesting to find out that there are currents throughout our planet that travel. If we can go on to the next slide, it deals with the currents, which are a pattern, a complex pattern that's simplified by this slide. The heat escapes more readily as it travels north. It actually is created, most of the temperature of the ocean is warmed at the equator, and as it travels north, it begins to cool, and as it reaches the poles, both north and south, the temperature, the current is driven down, and we'll see a demonstration soon on this program about how salty, cold water sinks, warm water sinks into cold, salty water, and we'll see that shortly. The atmosphere warms as heat evaporates, and there is this dialogue that takes place between the ocean and the atmosphere. Sea spray and water evaporate, creating clouds and helping to cool the planet. Winds help to drive ocean currents, both warming and cooling the planet. And we can go on to this last slide, which is more complex, describing the same kind of ocean pattern, which is even more complex than this is pictured. But it looks at what is called the conveyor belt of the heat engine that drives the currents. Oceans are a mix of fresh and salt water. As the oceans warm around the equator, water evaporates and gets saltier. Salty water, warmer water is carried north by currents, also releasing heat. As water moves north, it's cooled and sinks, forming a conveyor belt of sorts. The ocean helps to moderate the extremes of cold in the north and hot in the equatorial regions. And the ocean stores more than 1,000 times the capacity than the atmosphere. We don't quite know exactly how the ocean will respond to the growing amount of heat-trapping gases. We know that it's warming. We don't know how much warmth it will take and what consequences that will have, and Lianna will talk about that shortly. But now we want to come back to a demonstration that Alan will conduct with warm water and cold salt water. Alan?
So what we have here is some warm, relatively fresh water, and let's see what happens when you take cold salt water, as you find on the surface of the ocean in certain parts of the earth. And if the camera can zoom in on that, that cold red salt water sinks like a stone down to the bottom.
Maybe you can hold that up and show people.
Well, I think we have the black background. Do we have a good back? How does it look?
I think we need, if we can zoom in a little bit more, it would be helpful.
Oh yeah, definitely, much closer. So you see the cold, salty water on the bottom.
And focus. There we go.
And we still have fresh water on the top. That drives the thermohaline. Circulation. Thank you. So that's what drives the thermohaline circulation. It causes that deep current that distributes heat throughout the oceans.
Great.
And
now Lianna.
Because the oceans cover so much of our planet's surface, it's crucial to understand the role the ocean plays in regulating or changing Earth's climate. The ocean currents function like the human circulatory system, carrying life-giving nutrients and heat around the planet. Critical to the ocean's ability to maintain this circulatory pattern is the amount of ice contained in it. Because of this, we'll take a look at the relationship between global ice and sea level. Lew has given us an overview of thermohaline circulation, also referred to as the ocean conveyor belt. If we want to understand just how much heat, nutrients, and minerals the oceans are carrying and turning over, let's examine a part of the Antarctic circumpolar current. The ACC, drawn here in a black line, connects the Pacific, Atlantic, and Indian basins and is the strongest current system on the planet. At the Drake Passage, which is an area of ocean between South America and the Antarctic Peninsula, it has been estimated that the upwelling, called transport, of cold salty water to near surface levels is 135 times the transport of all the world's rivers combined. Only a few places around Antarctica and the northern Atlantic create water dense enough to sink to the ocean floor, making Antarctic bottom water crucial to global ocean currents. The Australian government-funded Marine and Atmospheric Research Centre recently released data on the salinity of the Southern Ocean around Antarctica, showing a significant freshening of the deep water. This could be a sign, the Australian scientists warn, that the overturning circulation system in the world's ocean might be slowing down. The National Oceanic and Atmospheric Administration has also measured declining levels of salinity in the subpolar seas bordering the North Atlantic. It's the largest oceanic change ever measured. Sea-based ice we find extending into the ocean from both the northern polar areas around Greenland and the southern polar areas around Antarctica. Although floating ice does not change sea level when it melts, any more than a glass of water will overflow when the ice cubes in it melt, that floating ice lacks salt. So when it melts, the ocean gains fresh water, decreasing the salinity of the sea. And remember that ocean currents flow mainly due to the cold, salty water sinking. So if we change either one of those qualities, if we warm the ocean or if we decrease salinity by dumping loads of fresh water in, the conveyor belt will not work quite the same. That's why we may be concerned that these massive sheets of sea ice, when gone, or if they're gone, will lower salinity levels enough to disturb ocean circulation patterns. The IPCC, the Intergovernmental Panel on Climate Change, had 18 computer models predicting differing amounts of sea ice loss for the year 2007. The National Snow and Ice Data Center and the National Center for Atmospheric Research have recently reported that loss of sea-based ice in the Arctic region in this past year was a good 30 years ahead of the computer models. What does this mean? Well, the IPCC estimated an Arctic free of summer ice sometime between the years 2050 and 2100. Now it could be looking as early as 2020. What about land-based ice? It occurs on all the mountain ranges you can think of. It makes up the glaciers in Alaska, and it's the permafrost areas of Greenland and the Antarctic that have land under them. Let's take a look at freshwater glaciers. When Glacier National Park was created in 1910, it was home to an estimated 150 glaciers. Since then, the number has decreased to fewer than 30, and most of those remaining have shrunk in area by 2/3. A scientist from the U.S. Geological Survey Global Change and Research Program predicts that within 30 years, most, if not all, of the park's namesake glaciers will disappear. It's a similar story everywhere else on the planet. The famed snows of Kilimanjaro have melted more than 80% since 1912. Glaciers in India are retreating so fast that researchers believe that most central and eastern Himalayan glaciers could virtually disappear by 2035. Permafrost is thawing all over Alaska. Greenland and Antarctica are the two biggest ice houses on the planet. Here we see a depiction of Greenland's ice loss from 1992 to 2002, which was substantial. And it is now documented by NASA's GRACE satellite gravity mapping imagery that Greenland has lost 3 times as much ice as it has gained between 2003 and 2005, as much as 57 cubic miles of ice each year. Part of Antarctica's Larsen ice shelf broke apart in early 2002. Scientists have used GRACE satellite data to show that the Antarctic ice sheet has shrunk by an average of 36 cubic miles per year between 2002 and 2005. It's believed that places like Iceland have been the home to glaciers for at least 2 million years. That means glaciers have stuck around even when the Earth was much warmer. Many scientists are estimating that Iceland's glaciers will be virtually gone within the next century. To visualize how much global ice has melted in the recent past, let's review a NASA estimate. Since 1960, glaciers around the world have lost around 2,000 cubic miles of ice. That's approximately enough ice to cover more than a 1 mile wide, 1 mile high swath of land from New York to Los Angeles. Imagine that. To put it simply, when temperatures rise and ice melts, more water flows to the seas from glaciers and ice caps, and consequently ocean water warms and expands in volume. The combination of effects has played the major role in raising average global sea level between 4 and 8 inches in the past 100 years, according to the IPCC. Sea levels have risen and fallen substantially over Earth's 4.6 billion year history. But the recent rate of global sea level rise has departed from the average rate of the past 2,000 to 3,000 years and is rising much more rapidly. It can take up to 1,600 years transit time for one molecule of water to complete a full cycle through the ocean currents. This is why some researchers speculate that we may not see the full effects of rising sea levels due to substantial global ice loss for a few centuries. However, many of these scientists also warn that too much change in ocean temperature and salinity could disrupt the North Atlantic thermohaline circulation enough to slow down or possibly halt the conveyor belt, causing drastic climate changes in time spans as short as a decade. This past March marked the beginning of the International Polar Year, a time in which scientists, doctors, and students from 60 nations will be studying both polar regions. Researcher Mary Alpert informs us that 70% of the fresh water on our planet is locked up in Antarctica, which she warns may be free of all ice within this century. Imagine, from what we have learned on this program about the ocean conveyor belt, what would happen if 70% of the Earth's fresh water were in the sea. Would the conveyor stop? Will the lack of fresh snowmelt water cause a drinking water crisis? How much will sea level rise? And how will it affect the 100 million people worldwide that live within 3 feet of mean sea level? We can see from these images that ice occupies much more space in the Antarctic region than does land. If the West Antarctic ice sheet were to break up, it alone contains enough ice to raise sea level by nearly 20 feet. The Greenland ice sheet holds enough water to raise sea levels worldwide by 23 feet. Now keep in mind that there's an estimated 10% of the world's population living lower than 32 feet above sea level. Large cities where human populations have concentrated near coastal plains or river deltas, such as Shanghai, Bangkok, Jakarta, Tokyo, and New York, are all extremely vulnerable to rising seawater and all the economic and humanitarian impacts it may harbor. Note that some of these images and are satellite photos in which it is easier to see how heavily inhabited the coastlines are. Some low-lying, densely populated, and dreadfully poor countries like Bangladesh could have no means to survive such a crisis. Even wealthier countries like the Netherlands could face serious hardship, with nearly half its landmass already at or below sea level. If Greenland melts completely, parts of America's coastal lands, Boston, New York, Los Angeles, will be underwater. And on that note, let's go to Leslie.
Thanks, Lianna. Thermohaline circulation, infrared radiation, IPCC. No wonder there's so much confusion about the issue of climate change. Our goal here is to break the information down into easily digestible pieces. We hope you'll join us for our next program of climate changes, where we'll be talking about carbon cycling through the living and non-living world and how it affects climate.